Okay, in this tutorial we are going to be looking at stoichiometry, which is essentially the process of being given information about one substance in a chemical reaction and asked to solve information about a different substance in a chemical reaction. So you'll see something like in this first example where you're given something like moles of KClO3, but you're asked to find moles of a different substance, in this case oxygen. So if I look at the chemical equation, I'm given information about KClO3, but I'm asked for information about a different substance, oxygen. That process of being given information about one substance but asked to give back information about a different substance, that process is known as stoichiometry. And we were introduced to this back in Unit 2. It's the idea of a mole ratio step. There's a mini tutorial on that. It was in your homework, it was on your test. But that idea of changing from one substance to a different substance can only be done in one very unique conversion step, which is called the mole ratio. And that's why we spent some time in Unit 2 practicing that mole ratio step in a smaller scale. So whenever we want to apply it to a bigger concept like stoichiometry, at this point you should be comfortable with it. So if we jump into an example, I have how many moles of oxygen are produced when 1.26 moles of potassium chlorate react, and then I'm given a chemical equation. For these problems, you will either be given a chemical reaction or you'll be told the names of them, and then you will have to generate the formulas. Again, that's why we do Unit 2 before Unit 3. Unit 2, your goal was to kind of really learn how to take those names and put them in the formulas, because now those formulas become equations and it just like snowballs more and more. So make sure that you have that understanding of naming and formula writing under your belt, because it's going to pop up over and over and over for the rest of the semester. So in this case though, the examples I'm going to do with you for the sake of time, I'm already just going to have the formula or the equation given to you. So for this particular one, we're starting with 1.26 moles of KClO3. So I'm just going to go ahead and start my problem with what I'm given in the problem. And I always take what I'm given and I put it over 1. And then my unit on top is going to go on the bottom. And then my question is, what am I going to convert to? So for this problem, I am just asked to go from moles to moles again. So it's just that one step, that mole ratio step. So moles of KClO3 is going to be on the bottom, and what I'm converting to is going to be moles of oxygen. And so the way now that I know what numbers are going to be put in here is I refer back to the balanced chemical equation. So if for moles of KClO3, I'm going to find KClO3 in my compound, or I'm sorry, in my equation. The number coefficient of 2 is there, so that tells me that I have 2 moles of KClO3. For my oxygen, I'm going to go ahead and find my oxygen in the equation, and the coefficient on the oxygen is a 3. So this is going to get a 3. And that's all. I'm just asked to convert to moles. So I'm there. I can go ahead, multiply across the top, divide by the bottom. I'm going to keep 3 sig figs because that's how many was at my starting number. And that's what you can generally plan to do unless you're told otherwise on the problems, is just run your answer to the number of sig figs in that given number. So I end with 1.89 moles of oxygen. Okay, so again, the key step here is we are looking at that mole ratio step. This is review from Unit 2. This mole to mole step is the only step that's going to allow you to change over that substance. So to actually change from KClO3 over to oxygen, you have to be in moles. And this one was a nice easy one because we're given the number in moles, we're asked to solve for moles, so it was just a straight up one-step conversion. If I look at my second one, we're going to expand it a little bit. How many grams of iron are formed when 13.6 moles of carbon react? Again, I identify this as a stoichiometry problem because I'm given my amount of one substance, in this case carbon, but I'm asked for amount of a different substance, in this case iron. So that process of being given information about one substance in the reaction and being asked for the amount of a different substance is essentially what stoichiometry is. The only way that we can go from one to the other is by using the mole ratio step. Okay, so we're going to go ahead with what we're given in this first problem. It's 13.6 moles of carbon. And I know that I want to change carbon over to iron, and in order to do that, I have to be in moles, so I can use that mole ratio step. And so in the second example, I am given the number in moles, so I can again jump right ahead or right on into that mole ratio step. So since moles of carbon is on the top, I'm going to put moles of carbon on the bottom. What I'm converting to on the top, which is going to be moles of iron. Okay, even though the problem asks for grams, I can't do that yet. The only step that's going to allow me to change from carbon to iron has to be moles to moles. And then if the problem asks for a different unit, I can continue that in a later step. But for this particular step, the only way I can change from one substance to a different is by putting moles on top and moles on bottom. So in order to get those numbers, I have to visit the equation. So carbon has a coefficient of 3, and then my iron has a coefficient of 2. Okay, and this is the only step in the mole ratio where the numbers of moles can be something other than 1. If you remember back to Unit 2, where we did all of our kind of introduction to the mole, there was that mole conversion chart. The number of moles is always 1. And again, the exception to that, and the only exception to that, is when you're inside this mole ratio step. And in that case, your moles come from your balanced chemical equation. So this step, this problem, I need to take it one step further. Right now, the moles of carbon canceled. I'm in moles of iron, but the problem asks for grams of iron. So I need to take it one step further. Moles of iron is on top. Moles of iron is going to go on the bottom. And recalling from Unit 2, moles to grams is something that I can do in one step. Outside of the mole ratio, the number that always goes with moles is 1. And again, back from Unit 2, you should know anytime you see grams, this should direct you to the periodic table where you have to look at the molar mass. If you look up the molar mass of iron, you will find that it is 55.85. And now we can go ahead and solve. Multiply across the top, divide by the bottom. Whenever I do that, I believe if I did this correctly, if I put this in my calculator, you should get about 506 grams of iron. Okay, and again, 3 sig figs, so I'm going to keep 3 sig figs unless I'm told otherwise. So I can follow my units, grams of Fe, that's where I am. Again, really in this Unit 3, this stoichiometry piece, when we're doing conversions, we did conversions in Unit 1, we did conversions in Unit 2, we're doing conversions again in Unit 3. The biggest step difference is going to be this mole ratio step. That's the key there that's going to allow you to change from one substance to a different substance. So we're going to do one last example of a stoichiometry problem. This one says, how many grams of lead nitrate are required to produce 122.1 grams of potassium nitrate? And then I'm given the equation. All right, so again, if I kind of look at what I'm given, 122.1 grams of potassium nitrate, but the problem is asking for how many grams of lead nitrate that I have. So I'm given information about the potassium nitrate, but I'm asked to give back information about the lead nitrate. So in order for me to go back and forth between those two, the only step that's going to allow me to change from one substance to the other is a mole ratio step. So in this problem, I'm given 122.1 grams of KNO3. And I'm going to go ahead and start setting up my conversion. Grams of KNO3 is on top, so that's what I'm going to put on the bottom. Now, I eventually want my answer to be in grams of lead nitrate, but I cannot. There is no step that allows me to go from grams KNO3 to grams of lead nitrate. It just doesn't exist. Because first and foremost, I know that the only way that I can change my compound and go from potassium nitrate to lead nitrate is by that mole ratio step. And in order to use that mole ratio step, I have to be in moles, which I am not. So my first step is going to be to take that grams of KNO3 and turn it into moles of KNO3 so I can use that mole ratio step. So this was back from Unit 2 when we learned how to do these conversions. Use it if you still want to get out your mole conversion chart, feel free if you still need that. Anywhere you see moles outside of the mole ratio, is the number 1. Grams, anytime you see grams, that's directing you to the periodic table where you have to add up the masses of each element in that compound, which if you do that, you should get 101.11. So that first step, I'm taking my grams to KNO3, I'm putting it into moles of KNO3. So then in my next step, I can use the mole ratio to change from KNO3 over to PbNO3 too. The only way you can change that substance is if you are in moles. So moles of KNO3 is on top, moles of KNO3 is going to go on the bottom, and then this is where, if I'm asked to change substances, this is where I now can do it. So moles of KNO3 to moles of PbNO3 too. And when they both say moles, I need to refer to the balanced chemical equation to find what those numbers are going to be. KNO3 has a coefficient of 2, so that's where the 2 is going to go. PbNO3 has no coefficient in front, so I can assume that that is 1. So that step allowed me to change over from the potassium nitrate to what the problem was asking me about, which is lead nitrate. Now, the last part of this question doesn't want to know how many moles of lead nitrate, it wants to know how many grams of lead nitrate. So I'm going to have one last step where I'm going to take my moles of lead nitrate and I'm going to go ahead and convert it to grams of lead nitrate. And now I can just go back to how I'm used to doing conversions, back to how we did them in Unit 2. So outside of the mole ratio, your number of moles always gets a 1. The grams is going to be the masses of all of those elements added up. So if you do that, you should get 331.22. Right, and now I can multiply across the top, divide by the bottom, and I can do that real quick. Into the 4 sig figs, which I will use unless it would tell me otherwise. I actually get a very fun number of 199.9899219. So in order to put that into 4 sig figs, I think it's going to be easiest for me just to do a scientific notation. And 200 would be times 10 to the second. Okay, and that should be your grams of PbNO3 too. Okay, so that's some examples of stoichiometry problems. Again, biggest takeaway from this, always take your given number, make sure it's in moles so you can use the mole ratio to change from the substance that you're given information about to the new substance that you're going to be asked about. That numbers from the balanced equation are only used in the mole ratio step. Outside of the mole ratio step, we're just using the number 1 with moles like we did back in Unit 2.